Welcome to solverfy.
Here we have a drawing of the titration of 30 milliliters of 0.1 molar KOH with 0.1 molar HBr. And we want to calculate the pH of the solution in the beaker at various points within the titration. First, let's look at the very beginning before any acid has been added. So we only have KOH in the solution, and since KOH is a strong base, it'll dissociate completely into potassium ions and hydroxide ions. So we can find the pH by solving for the POH, which is the negative log of the concentration of hydroxide ions. This is equal to 13, which is very basic, which makes sense. Now let's look at the pH once 15 milliliters of acid has been added. Using the fact that molarity is equal to the number of moles over the volume in liters, we can solve for the number of moles of HBr by rearranging this equation to get the number of moles is equal to the molarity times the volume in liters. So our moles of HBr is equal to the molarity, which is 0.1 molar, times the volume, and 15 milliliters in liters is 0.015. So we know we have 0.0015 moles of HBr, or 1.500 millimoles if we want to make it a little bit easier to write. If we do the same calculation with our initial amount of base, we have 3.0 millimoles of KOH. Since this is a strong acid, strong base titration, the acid and the base will react and neutralize each other fully. So 0.15 millimoles of HBr with 3 millimoles of KOH, we will be left with 1.5 millimoles of KOH. This is then in a solution of the initial 30 milliliters of KOH plus the additional 15 milliliters of HBr, which gives us a molarity of 0.03333. This is actually the concentration of KOH, but since there is a 1-to-1 ratio of KOH to OH, it is also the same concentration for hydroxide. So now we can find the pH the same way we did in the first part of this problem, and we get a pH of 12.52. And you can see here that the pH is decreasing as we add more of the acid, which makes sense since the higher the acidity, the lower the pH. Now let's look at this titration once we've added 29 milliliters of the HBr. Just like in the last part, we can solve for the number of moles of HBr, and we get 0.0029 moles, which is equal to 2.9 millimoles of HBr. And again, this will react completely with the KOH, and we will be left with 0.1 millimoles of KOH. This is in the solution of the 30 milliliters of KOH plus the 29 milliliters of HBr, which gives us a molarity of 0.01695. From this we can solve for the pH, just like in the first and second parts, and we get 11.23. Now let's see once a total of 29.9 milliliters of the HBr has been added. Again, solving for moles, we get 0.00299 moles, or 2.99 millimoles of HBr. Then, reacting with the KOH, we end up with a 0.01 millimole amount of the KOH. This is in a solution of 30 milliliters from the original KOH, plus the added 29.9 milliliters of HBr, which gives us 0.0001669 molar OH-. Again, we solve for pH, and we get 10.22. Now, once we've added a total of 30 milliliters of the HBr, we have an equal amount of moles of HBr to moles of KOH. These will completely react with each other and completely neutralize each other, and we'll end up with a completely neutral solution. And we can jump to the conclusion then that our pH is going to be the neutral 7. We know that this is the equivalence point because all of the HBr has reacted with all of the KOH, so there is none of either reagent remaining in the solution. Also, this is a strong acid, strong base titration, and each strong acid, strong base titration has a pH of 7 at the equivalence point. So what happens when we continue to add our titrant of HBr? Well, let's see what happens if we add an extra 0.1 milliliters. So once we have a total of 30.1 milliliters of HBr added. Well, let's start by converting to moles again. We have 0.00301 moles, which is 3.01 millimoles of HBr. This will neutralize all of the 3 millimoles of KOH, but we will still have 0.01 millimoles of HBr remaining. This is then in a solution of 30 milliliters from the KOH plus another 30.1 milliliters from the added HBr. And this gives us a concentration of 0.00016664 molar HBr. And this implies the same concentration of H+, since there is a 1-to-1 ratio of H+ and HBr. And now we can solve for our pH, since pH is the negative log of the concentration of H+, and we get a pH of 3.779. So now we've passed the neutral equivalence point, and we're continuing to add acid, making the solution's acidity increase, and therefore the solution's pH decrease. Now what is the pH if we have added a total of 40 milliliters of HBr? Well, this is 4 millimoles of HBr. So once it reacts with the KOH, we'll have an extra 1 millimole of HBr remaining. This is in a solution of 30 plus 40 milliliters. So we end up with 0.01429 molar H+. And this gives us a pH of 1.845. If we draw the general shape of a titration curve, then our first step here is at the very beginning. Our second step is once we've added a little bit of acid. Our third step is where we're almost to the equivalence point. Then our next step is even closer to the equivalence point. And step 5 is the equivalence point. And this is where we have a pH of 7. Then at step 6, we continue after the equivalence point. And this is where our pH starts to decrease below 7. And then once we get to step 7, we're at the end of the titration curve once the pH starts to flatten out.